Hi everyone, I'm Kwang-hee, a first-year master student working with Professor Shinji at CMU. Today I'm going to talk about our paper, Understanding Probe Behaviors Through Variational Bounds of Mutual Information. So it is a little bit mouthful, but I promise I'll try to be less math-heavy and quite practical. So I'm going to talk about probing stuff like linear probing. I'll start with the brief introduction on what is probing. Then I'll go over the various key ideas one by one and briefly discuss the experiments and finish it with the takeaways. This talk is meant to be a beginner-friendly guideline where I aim to provide an easy guide for y'all to try probing and interpret their results when you want to observe the hidden representations of self-supervised speech models. So let's start with the motivation. So what's probing? To start probing, we have to define a task first. We have to design a probing task where the task can't affirm or deny whether the representations contain that specific knowledge or not. For example, if we want to check whether the self-supervised learning models understand phonemes, then we simply define the task as phoneme classification so that higher the accuracy, more information inside those representations. So how do we actually probe? Basically, poking around things in a cheap way is probing. So in our case, probing is poking around the frozen deep learning models, especially the layer-wise hidden representations, checking each layer's outputs and looking at their trend. We attach the probe to the model and train only the probe, which is often very lightweight so that we can easily poke around. The common setting nowadays is use classification as the task, single linear layer as the probe, and observe the layer-wise accuracy. So to recap, we freeze the model that we want to observe and attach a learnable probe and train that probe with a well-designed task. Then we observe the predicted performance of that probe per each layer. So let's start with the actual content. First, let's briefly cover the information theoretic understanding of classification, as classification is usually used in probing. So probe takes the label Y and the ith frozen representation HI, right? To train the probe, if you're minimizing the classification loss, the cross-entropy loss, it is equivalent to maximizing the mutual information between the label Y and the hidden representation HI. Let's formalize this a little bit more. So the mutual information between the label Y and the hidden representations HI is exactly the same with the classification loss value, where F star here would be the ideal probe. This is literally the ideal situation, so that we are assuming that the probing network actually found the optimal function. In other words, it minimizes the cross-entropy loss perfectly. We can't minimize loss more than this. However, our life is not that easy, so that oftentimes the neural network is an approximation for the optimal probe F star. So the empirical loss is always bigger than the ideal loss. In other words, the mutual information estimate is always smaller, at most exactly the same. This idea is very important, so let me explain it once more. We are training the probe by classification, which is an equivalent to mutual information maximization. The loss aims to approximate the optimal probe F star with the neural net approximation F theta. However, as there will always be difference with the optimal probe F star and the empirical probe F theta, the results will be always estimates, at most the exact values. So in loss terms, estimate is always bigger. In mutual information terms, estimate is always smaller, underestimating the mutual information between Y and HI. So with this basic idea, we can actually extend it to quite a lot. In the end, linear probing or mutual information maximization aims to approximate the optimal probe F star with the neural net F theta, right? The key observation here is that the formulation does not limit the definition of F theta. The only thing is that we want to make F theta as close as possible to the optimal function F star. So in this sense, let's look at fine-tuning. So it's pretty straightforward, freezing the layer 1 through I and unfreezing the remaining to fine-tune it. Let's compare it with linear probing, quite similar. Actually, the formulation is equivalent, and the only difference between the two is the capacity of a theta. As the network capacity is bigger for the above, it is more likely for the above to be more closer to F star. In other words, having a bigger, better mutual information estimate. Except for those empirical differences, it is basically equivalent. So, if you actually run linear probing and draw the layer-wise accuracy curve, the mutual information per each layer, oftentimes it peaks in the middle. So it's like curved. Some says that like pre-trained weights are so good that it adds knowledge so that the information increases. But actually this is against our mathematical formulation because deep learning models are lossy channels and we can't have more information than the one we started with, the mutual information between y and x, and it always has to be decreasing at most constant. Then how can the lossy channels somehow rediscover the label information from the intermediate representations? How are the information somehow like magically restored? Actually, we have to keep reminding ourselves that those are estimations, not true mutual information values. True mutual information values should always be like not increasing due to deep learning models being the lossy channels. And our mutual information estimations are always lower than the true values. And it is likely that this estimation differences decreases for the later layers. In other words, the empirical probe gets more closer and closer for the later layers. In other words, the representations become more friendlier for the linear probe. Again, the information is not magically restored. This behavior is quite interesting because there is a clear trade-off. Later layer always loses information, but it becomes much more friendlier for the linear probe. Actually, this motivates the idea for measuring the goodness of representations on like quantifying what is actually a good representation. So the key idea would be maybe the linear separability, the margin between different classes, was actually the factor that we were referring to as good to use. In this sense, like using linear probing is actually not a bad idea, even though it will yield worse mutual information estimates than most more and more bigger probes, like fine-tuning. Actually, we provide a proof in the paper that bigger linear separability margin yields a more accurate estimate. The difference between the estimate and the true value decrease for later layers, right? Not only we think it is due to the linear separability, but also the margin of separability seems to matter. There are more details in the paper, so feel free to check it out. Finally, this will be a super easy fix for existing code bases. Use the loss rather than accuracy. Like, recall that we were already estimating mutual information anyways, so why not use that directly? But does that mean that existing probing results are all bad? Not really. It's because it's kind of okay to use accuracy, even though it won't be as accurate as using losses. We also supply a simple theorem that implies accuracy is quite a loose bound, even though it won't be that loose in practice. So we finish our talk with demos and takeaways. We chose cross-lingual word classification task as the toy example for demonstrating our claims. We use the common phone dataset, which has like word alignments, and the XLSR model where we slice the audios so that each audio contains only the word utterance. So the hypothesis is that we want to first show the curve behavior first and test different probes with different capacities and compare the accuracies with the loss. And the results would be this, and let's look at this in detail. For the first hypothesis, let's look at the left figure first. The blue line is the linear probing. We can easily see that curved behavior. For the second hypothesis, Other lines show like different network capacity, MLP probing being a little bit bigger and fine-tuning being a lot bigger. So it shows that the estimate gets better as capacity increases. In other words, curve behavior slowly gets removed. Finally, let's compare with the left and the right figure. Left is the loss, right is the accuracy. Even though that the trend is very similar, we can see that right side shows a slightly wrong ordering for the probe size. Finally, I wrap up my talk with two takeaways. The first takeaway is about the common potential misunderstandings when using probing. Some says that we shouldn't use big probes because bigger probes will yield better accuracy and possibly just memorize the task if the task is too simple. However, recall that the formulation of theta didn't contain the specifics of the model. What probes have to do is to check whether that specific information exists within that hidden representation, no matter the cost. In fact, we saw that bigger the probe, better the estimation. Also, we observed the curve behavior, the peak mutual information in the middle. Some says that pre-trained weights are so good that it adds knowledge so that information increases. However, recall that knowledge being added violates the information theory. Deep learning models are, however, recall that knowledge being added violates the information theory, and deep learning models are lossy channels, so we always lose information. Then, why those curves happen? Because it is likely that the representation becomes more well suited towards linear probes, being separable, being with enough margin, not being added new information. The second takeaway is about the good practice for probing. When you try probing, just use losses, not accuracy. And just remember that those estimates are lower bound estimates. And we also discussed about what would be a good representation to use. We observed an interesting trade-off between the information existing and whether it is actually linearly separable enough with enough margin so that it is usable for us. Finally, we also compared fine-tuning with linear probing. Fine-tuning is a method easy to implement to yield good mutual information estimates, and linear probing additionally measures the separability and the margin, so it needs to be a little bit more careful, but nevertheless useful. It was Kwang from CMU at Shin's Wave Lab, and thanks a lot for your attention.